title is Eternal Sunshine of the Spotless Macro because my favorite metaprogramming topic are macros, but obviously I will not start about macros. So at least how many of you have heard the term macro in the context of programming? Okay. Like in C, for example, but these are the bad ones. Okay, we'll talk about metaprogramming. And so I'll give you a bunch of definitions. So metaprogramming is a technique when a computer programs have the ability to manipulate programs as their data. This is the most general definition that you find everywhere. It's like a technique where computer programs have the ability to manipulate programs as their data. And this seems quite easy. I mean, you can easily write a program that takes another program and does something with it, right? So it doesn't seem particularly special. Obviously, how you do it, and for 99% of the definition I'll give you today, there's always an interpretation that seems trivial, and there's always one that is actually the one that people mean. And this is the first one that I'm going to give you. So, a program can be designed to read, generate, analyze, and transform the program, including itself, at compile time, at runtime, or both, in any combination. And still, this is a form of metaprogramming. So if you want to be very general, anything that analyzes program can be a form of metaprogramming, if you want. Now, the language in which a metaprogram is written is called a meta-language. So usually, there are specific and dedicated meta-languages that allow you to do metaprogramming. But today, we'll try to see the ones that actually, where the programs you analyze and the language used for metaprogramming are actually the same. So one of these definitions that is not universal, again, is this one. The ability of a programming language to be its own meta-language is called reflection or reflexivity. I'll give another definition of reflection that maybe matches a little more the ones that you know from, for example, from Java, but that's the idea. So it's not a novel technique. It's something that came, so this is taken from a survey, and there's plenty of stuff there. So the first metaprogramming elements that you will see, they come from 1965, okay, on the Lisp macros. And there are things up to nowadays, there's still macros, the latest in this timeline, the ones on Scala, but nowadays, macros, for example, are in many languages, for example, Rust, that is actually used for system programming mainly, Elixir, and what was the other one? Julia, which is used for numerical computing, and it's quite popular in that domain. But there's a lot of other things, and I'll cover some of them. There are even for, well, there's Smalltalk, very important here. There's Scheme somewhere, there's MetaOcamo, there's Java in the reflection side, and so on and so forth. There are a lot of families of languages, very different ones, and all of them have somehow some form of metaprogramming, most of them. So the paper where I took that timeline actually proposed a metaprogramming model. So of different kind of systems and let's say flavors of metaprogramming, and these are the ones that I will talk to today. We will go through and we will see they are all connected with each other until arriving to macros. So let's start from reflection systems. A reflection is supported when a programming system can reason about and act upon itself. So this is slightly different than before, but it can match the definition that I gave before. We can discuss about it. Modifying its own structure and behavior, and typically it's meant at runtime in this case. At the end of the talk, I'll show you even how you can do reflection at compile time. So there are two kinds of reflection features in order to have full reflection. One is introspection, one is intercession. So introspection is when you have the ability to, let's say, explore, examine, and navigate the structure, the representation of your program itself. And the structure can be quite complicated. Intercession instead is the ability to modify it. Okay, these two are typically two features. In the best cases, you have both. In the worst cases, you have one of the two. Guess which one? The one on top, introspection. So I said structural, but actually reflection can be structural or behavioral. If it's structural, if you can introspect or intersays the structure, so the classes, the method, the attribute, the static structure of your program. It's behavioral when you can actually do the same with the representation or with the representation of dynamic relationship. For example, the relationship between an object and its class, pointers and stuff like that. If you can do something like that, then you have structural reflection. So I want to show you how you can do that, first of all, with Smalltalk, which is probably the best existing, apart from a scheme, for example. It's another alternative. Language that has introspection and intercession in a complete way. So here you have an object. I'm just calling a constructor here from a class and a method, nothing more than that. This is like a representation of the object that has been just created. This is a live environment, so you see the result of this computation here. And then I can, for example, take the class of that object, and I have a representation of its class. This you can do it also in Java, for example. I can access the list of methods, and this is like a collection of all its methods, and I can call a collect, which is a map in this case, extracting the lines of code. And here I have a collection where I have a number for each method and corresponds to the lines of code. I can take and compute the average, okay? And this is like structural, the typical structural introspection you can do, but you can do introspection also from a dynamic point of view. In this case, I can take this context that represents the dynamic context in this particular execution time. So in this case, it's in this notebook, if you want. And there I can, for example, extract the stack trace. And I can take the compiled code that corresponds to the code that I've just done. Okay? So this is, obviously there are methods here. There's some corresponding source code, which is exactly the same that I actually executed. And there are methods here, there are versions, well, it's not that important. So you can actually do a lot of stuff. With intercession, you can do more. So here, I'm calling a method on the object, which is the top class in Smalltalk. Not exactly, but when you want to create something related to OP, it typically is. And I'm creating a subclass. I'm calling it hello world with no instance variable names, no class variable names, so no fields, pretty much, and a category, which I always forget what it is. And I get a class. And I'm getting it at runtime. This is like a new class in my system. And then, yes, I can add a method. In this case, by compiling this hello method that returns hello. This is syntax. This is Smalltalk syntax as a string, pretty much. And then I can call it. I can call it in different ways. This is with perform, or I can actually create the object and call it. And that's it. And I get a string, obviously. So I created the class from scratch. I added it a method during compilation and so on and so forth. This is typical forms of intercession. Yes. So this funny piece of code that you will see in a sec will do the following. I create an object of type, and I call it foo. Obviously, if I try to, this is like a new object of the top class, so it has no feature, no method. So if I call it, for example, the method hello, I cannot do anything. What I can do is I can change the class of it, and I can, in this case, assign it to hello class. So the class that I just created, and now hello. Huh? Doesn't work. Huh. Let me try. Did I do this? Okay, this doesn't work. And now it should work. Yes. Okay. And now the type of that object obviously responds to hello, so because I changed the class of it. So these are the things that you can do with introspection. And so these are the typical features that you have with introspection, intercession in typical languages. In Smalltalk you have everything. In Lisp dialects, in most of them, you have everything. And in Java, what you have is only a complete form of structural introspection, but no behavioral, no intercession for structural, only some support for behavioral intercession, but from the paper I could not exactly understand what the authors meant. So it's probably due to what you can do with class loading, but I'm not 100% sure. So this is it. Let's go on and let's talk about meta-object protocols. So when you do things like reflection in general, you have APIs in object-oriented programming that allow to do those operations that I showed you. And in fact, this meta-object protocol is just the API that enables typically full-fledged reflection. And it's important because it matches typically the semantics of the object system itself. In this beautiful book, there is by Quixales, is one of the best books on this stuff, on meta-object protocols. So on the APIs that I showed you before, pretty much. But what happens is that obviously you can see them in a live programming environment as a deeper thing that allows you, for example, to transform the language behavior in its implementation, okay, in a deep way. What I want to show you now is that the shape of this API allow you to talk about things like meta-classes. And in this case, for example, this is the typical model that you have in Smalltalk. If you have an object, you go to the meta level, you get the class, and this class can be represented by itself as an object, like we did before. And if I use the method of its class, which is a meta class, I can modify it. So before I created, for example, I added a new method to a class. I did it through a method of the meta class with some parameters, and that reflects the changes to the object that belongs, that is an instance of that class. But this is not the only method. There are languages where actually you have mirror objects, that are not exactly mirror object, this is a different concept, but you have objects on the meta level that are different from the object and the class, and this allows you to do funny things. So this is the case, for example, of Ruby, when you have a meta-object-based approach, and then a single object, any single object, has a specific form on the meta side, and any class has obviously a specific meta-object on the meta side. And these are called eigenclasses. And now I'm going to show you how it works because it's different from Smalltalk. So I have a class, is it big enough? I hope so. I have a class lupus that does woof, something like that. And then I have a method, make me quack, that takes an object or a class, and it accesses the eigenclass of it, and it defines a quack method that returns quack. Okay? And I can pass it, for example, I can create a new lupus, another wolf, and I can make quack the first lupus, and if I print it, there will be some result. So Ruby eigenclass RB. The first wolf quacks, and the other wolf, it doesn't respond to quack, so it doesn't quack. It will throw an exception if I try to do that. Now, this obviously, if I now do the same with the lupus, so passing the class, what do you guess will happen? Right. This is the difference. The eigenclass of lupus adds methods at the class side. So I added a static method in lupus. This is a completely different thing. So in fact, now I can do lupus.quack. This confused me a lot at the beginning. So there's not the same to do the same thing that I've done before, you need to do something like this. This make all quack takes a class, and then you do a class evaluation. So you pass an expression to this method evaluates it like it was inside the class, and then it defines a quack for all the classes. So if I make all quack with lupus, then I can do something like this. And both are quack and true. A completely different model for this. I don't know where it comes from, but exactly. But Ruby is original for many things. This is one of the many. So And I'll talk briefly about generative programming, which is another flavor of metaprogramming, and it works like this. Yes. It's a paradigm again, where what you do is you try to generate out the program to some algorithm and some program representation, typically the one of an AST. So like play the role of transformer, if you want, of ASTs. But when you talk about generative programming in general, you mean it with a clear distinction between normal code and metacode. If you've seen any research, for example, that is done in the Netherlands, there are plenty of examples of systems that can allow you to inspect code and manipulate it. And Rascal is one of these. But I want to show you how you can do it inside a language without having anything special. So the typical approaches are based on AST transformation and compile time reflection. And I'll show you now what you can do with AST transformation with Groovy. Does anybody here have ever programmed anything in Groovy?
Hello world. Yes.
A hello world. Okay, Groovy is cool for many reasons. One is what I'm showing you now. So this main Groovy, it looks like Java. It's a little more lightweight. What you have here is pretty much a main method that calls a greet, and this greet is annotated with this @with logging. This @with logging is an annotation like in Java, but this annotation is annotated with some stuff. This Groovy AST transformation class. This is quite similar to what happens with annotations in Java that are processed with the Java annotation processor, with a great difference. Let's see what happens here. So here I have a string that actually represents a method, and this, a class that has a visit that takes AST nodes and some source unit. This allows pretty much to inspect the code structure of the method that has been annotated and do something. This method creates two new statements, for example, start message and an end message, and it puts it at the beginning at the end. Have you seen anything like that done with any other programming system or paradigm? Like putting logging before and after? Yes? Aspect-oriented programming, exactly. This is like doing static AOP without having all the infrastructure for that. And AOP can be seen as another way of doing metaprogramming, but that can be questioned. So, and here there is some method calls in APIs that create an expression, okay? Why do you think this is bad? So I've seen ways of creating code with strings, ways of creating code with code, like in case of Ruby, and this is another way with methods, pretty much. Is this good or bad? What do you think? Which of the three is better?
This is a little bit better.
Better?
Yeah.
Do everybody agree?
The second one.
The second one, why?
Because it's Ruby.
It's Ruby, okay. Ruby is cool, Ruby is awesome. I agree. But why? Because it's representation like all the other code, right? Like normal code. Here instead you have to do this, you create a new expression, then a method call expression. If by mistake you make an error, it crashes during, in this case, during compilation, okay?
That's why I would say that this is still better than strings, right?
Then strings, yes. Yeah. I agree.
I thought about this.
I agree. No. I was comparing all this. Okay. So, yes. So this is what it does. And compared to what you can do in Java, so the bad thing of Java notation processing is that what you generate, it's a source file, so it's a string. You can inspect the code that is annotated with the typical API like the one that I showed you, but the code you generate is not even generated with an API like I showed you in the case of Groovy, but you need to generate a text file, which usually is bad. You need to typically use an intermediate thing that then will generate the code. And this is not it. Finally, we arrive to macros. So a macro is a pattern that specifies a certain input sequence should be mapped to an output sequence that replaces it. And this is, again, is so general that you can think about the C preprocessor, and it's a macro. It's totally a macro. But And the process that transforms a specific macro pattern into the resulting output sequence is called a macro expansion. Other things that you may be used consciously or not are things like M4, for example. When used for generative programming, macros, instead of the process that we have seen before, it tends to blend the meta language and the language. So before we had APIs, or we had strings, and in the case of Ruby, obviously, we had already code, even if we didn't have macros in that case. But with macros, you blend the language and the meta language, coherent with reflection principles. And this is languages that support more or less macros. So at the lexical level, pretty much you consider the patterns at the level of tokens in the programming language, so they are not very interesting, and they're based on patterns. While the one on Lisp, on classic Lisp, they are syntactical, so at the level of the syntax, and the transformation are expressed through procedures, through normal code. In the case of Scheme and Racket, you have more. You can do it actually with patterns, and they are hygienic, and I will tell you what it is in a second. With Scala is almost the same, except they don't work with pattern, they work with code, and the same is with Julia and Rust, with the modern languages. So how does it look like? No, first of all, I will tell you what is hygiene. Obviously, when you try to substitute code and process code, you need to have some kind of guarantees. Typically, the ones that the expansion never introduce any form of name conflict. So the variables are like are not touched by the macro expansion. Otherwise, you may have collisions, for example, and the semantics, so you can break the code that you try to modify. So, how do macros in Scala 3, but also in Julia and in Rust, they work very similar. So, you have a type expression of T, ignore the plus. Well, if you want to know, this means that it's covariant on T, which is quite natural if you know what covariance is, but it doesn't matter, it's an expression. And you have this represented as a type in your language. And it's the meta side that gives you some help. And you can do splices and quotation pretty much using code, like you would do splicing and quotation, but with strings. So instead of using strings with macros, use it with code. So if E is an expression of type T, then $E turns it into an expression of type T that can be used in normal code, okay? With code, you do the opposite. If E is an expression of type T, the quote of E represents the typed abstract syntax tree of E. So from AST to normal expression and vice versa. So that's what it is. I want to show you briefly, and then it will be the last part, how do they look like, maybe. So, yes. So now I will show you, let's try. I will show you a little piece of code of very simple, relatively simple, let's say, DSL that I show to the students in my course. This is like an assertion DSL that can be used for testing. So this is like a method that takes a list of expressions. This expression gets automatically translated with macros into assertions. And actually I'm using a lot of stuff from Scala, and the first two lines that you see here in the report is actually the translated stuff. It's an assert that list not empty is actually true. And here I have a fluent method of this assertion. This says, the language says something like the list of 1, 2, 3 should be non-empty. So it reads like fluently, like many DSL. And if I have a look to the like the semantic of the should method, there is nothing. So at runtime, the should method does not exist. The semantics of it, it's a complete program transformation semantics that is done in this assertion method. This assertion method takes a bunch of things. It's an inline. It means it tells the compiler, look, whatever you take as a result of this method, you inline it where it's actually being used. So it's actually not called at runtime. It's inlined during compilation. And here you have a splice what you call the actual macro, and here you take the expression that represents the assertion and you take it at the meta level. If you look at what this method that actually implements the macro as a signature, is the following one. It takes an expression of this assertion property class, so an AST, and returns an expression or unit. An AST, but it's pretty much void. It's a set of assertions, so it doesn't really have a type. So let's ignore this for a second. So what I first do with macros, what I can do is inspection, right? Not only just create expression, but I can actually do introspection of these expressions, and I can use pattern matching for this. This is a typical recursive thing, so I say if my expression is an assertion, and I can even impose the type that it is, and some remaining part, because this is a list of expressions in the end, then I can rewrite it recursively. Otherwise, I rewrite the single assertion. If I have a look to this, for example, it does pretty much the same. It takes the expression, and it does pattern matching on that. And this is like in the form of a quote. So if I have a subject expression, so what I want to test with the subject type that I'm also extracting should be, and here I'm doing some magic. Here I'm extracting the method name pretty much. What I do, I have another method that does some magic and rewrites it in the assertion that I showed you. The magic is quite complicated, but I want to show you just at the end. The assertion is really expressed as a piece of code, as an assert, where I put the code that I want to do, which is actually the subject and the method call. And then I can even use, I can even create some dedicated, some custom some custom message if the assertion gets violated. Then I return it, and that's my whole macro. So what I've done, I've inspected the source code, I have transformed it, in this case, into assertions. So the cool part of this is that obviously, in a way, it's the same as in the expression trees that are in PF2. There is something there that is not part of the expression, and that here I have extracted in a certain way, which is, for example, the method names, right? These are things that in Scala, like method symbols, class symbols that you want to use, you cannot splice it and insert it. You can really work only with expression. So only with arguments, only with things that are part of expressions. If you have a method call, for example, you can actually use it in pattern matching, but the method needs to be named, okay? You can extract the object, the subject maybe, the arguments, but you cannot extract or you cannot splice an exact method name. In order to do that, what you do is you go into the same level of abstraction that we had in Groovy, if you want. It's a better API, but this is like constructing untyped ASTs with an API, and this is part of the reflection API at compile time that you have in Scala. In that case, what you can do is you can actually, for example, take a type, take the corresponding class, get the method symbols, and then construct whatever AST you want. Obviously, you lose a lot of stuff, like for example, while this can be type checked, while I program, this will be type checked only during macro expansion, okay? So this becomes a little more complicated. But again, it's transformation. Just to finish, because I don't have time for the last part, I want to show you this version. I will not tell you how I did it, but this is a variant of that. And the variant works like this. So this works pretty much with methods that return Boolean. Now I want to write down a little DSL that works pretty much with any property, right? You have, for example, getWeight in this box class. It's not really getWeight, but it's like a property, okay? This is a case class, so this is like a record in Java. I have weight, and I could say, okay, the box should have weight equal to 30 kilos. What is difficult here? The difficulty here is that this weight, by the way, it's a method. I almost finished, sorry. The weight method is actually a method, but the method is not really known at, so it depends on the type you're testing. So this is a method, okay, that is part of my DSL of testing, okay? But this method depends on this type, otherwise it shouldn't exist, right? The same could be, for example, I have a complex class here that has RE and IM, real and imaginary. Just my DSL. And the same happens here. So this method depends on the type I'm testing. Okay? In order to do this, you need to do something that is called a type provider. So this shoot method creates a dedicated type that it's in function, imagining like a class, in function of the type you have on the left. So if this box has a property of type, mass, that is called weight, it creates a method weight that takes some mass. And this is something really advanced that you can do with macros. It's messy, but here you see the methods that I'm generating. For every property, I'm generating this def weight, for example, that takes a mass, or also other stuff that I shouldn't generate, or price, or label, and so on and so forth. This actually is something called type provider that is coming from a language called F#. It's done in a completely different way, but that is also a form of metaprogramming that I found it extremely cool. So this is just to give you an idea. I had the last part. If you're curious, we can talk about it, which is a bonus on multi-stage programming. So with multi-stage programming, you move the meta level at runtime, okay? Instead of expanding during compilation like I showed you, and the example will be easier in this case, you can actually do it at runtime. What does it mean? Here I have this method. So pretty much it's a stage power. It's a power, it's calculating the power, and it's, calculating the power, and it's doing it with metaprogramming in order to optimize it. So it optimizes it. So this is like a stage power of 2. It returns a function from double to double that does the square power pretty much. If you run it, you will see the compiled version. The same happens with the stage power of 3 and stage power of 4. So the stage power, what it does, it creates some piece of code where pretty much only the n is fixed. The initial argument is not fixed because obviously it depends on the specific n. It does the optimization, in this case by, for example, if n is equal to 0, it rewrites it automatically to 1. So it calculates it as an expression with a constant value. If it's 1, it's x. If it's 2, it's x times x. And in this case, it guarantees that you will always do a number of multiplications that is logarithmic in n, okay? I'm not wrong. Now, when I compile it, so when I run it, well, I should have compiled it. So, wait. If I compile it, normally I would have something that would say that there is any macro expansion, but there's actually nothing. If I run it now, what will happen is that this will print the optimized version of this function. So n times 2 is just x times x, and this is like compiled and resolved completely at runtime. Times 3 is x times x times x, and n times 4, sorry, power 4, it is y equals x times x, and then y times y. So this is like the optimized version, okay? So in this case, I've used, I have this pre-compiled. Imagine I'm using it a certain number of time during the execution. I will have the optimized version created once and reused many times, okay? But this is just because in this case, I could move this optimization at runtime when I know actually the values of n, because the compilation time, I might not know them. In this case, I do. So this is just a toy example, okay? This is it. I showed you many models. Actually, they are interconnected in the ways the ideally code. So you start to do certain things at the meta level, and you wanna stay, especially in these cases at runtime and in the case of macros, as close as possible to the code that you normally use and on no meta level. And this is what I found it extremely cool. Thank you so much.